In this module, we will discuss testing for differential expression in a high-throughput genomic experiment. As a reminder, we have already discussed the pre-processing methods including image analysis for array-based data and alignment for RNA sequencing-based data, normalization, and expression summaries. Once we have expression summaries, we then perform our planned statistical analysis. We will now focus on the task of differential gene expression analysis, a commonly planned analysis for high-throughput gene expression data. There are two large taxonomies describing analyses of high-throughput genomic data, which are referred to as supervised learning and unsupervised learning. Supervised learning incorporates knowledge of phenotypic information of the samples being examined. For example, in general situations where there are two known classes or phenotypes, such as healthy versus diseased tissue samples, differential expression is when one wishes to determine whether there are significant differences in gene expression comparing the two classes. Additionally, differential expression analysis may be applied if there are more than two classes under study, such as comparing the expression among the 4 tumor node metastasis stages for a solid tumor. Thus, differential expression is also referred to as feature selection. Supervised learning also encompasses identifying genes related to a quantitative phenotype, such as high blood pressure, as well as class prediction, that is, finding a multivariable predictor of group membership. Unsupervised learning refers to an analysis where phenotypic data are either not available or are not used in the analysis, and the goal is to use only the expression values to discover structure in the data, such as clusters. When the phenotype is a factor with two levels, such as healthy versus diseased tissue samples, and the samples are independent, if one wishes to determine whether there is a significant difference in gene expression comparing the two groups, a two-sample t-test or its nonparametric counterpart, a Wilcoxon rank sum test, may be performed. If there are more than two groups being compared, either analysis of variance or its nonparametric counterpart, the Kruskal-Wallis test, may be used. If the goal is to identify genes significantly associated with a continuous phenotype, like blood pressure, linear regression is commonly used. When interest is in identifying genes that are differentially expressed when comparing two groups or conditions, the null hypothesis is that the two group means, denoted by mu sub 1 and mu sub 2, are equal, while the alternative hypothesis is that the two group means are not equal. A statistical test of hypothesis is a procedure for assessing the compatibility of the data with the null hypothesis. The data are considered compatible with the null hypothesis if any discrepancy from the null could readily be due to chance alone, that is, due to random sampling error. Data judged to be incompatible with the null hypothesis are then taken as evidence in favor of the alternative hypothesis. When judging whether the data are compatible with the null hypothesis, obviously if the sample means are calculated and found to be identical, we would suspect that the null hypothesis is true. However, even if the null hypothesis is true, we do not really expect the sample means to be identically equal because we expect there to be some variability due to sampling. We would feel comfortable concluding that the null hypothesis is true if the difference between the two sample means does not exceed a couple of standard errors, because that can happen by chance alone. Because we use the means and the standard error of the mean difference in the two-group comparison, as a reminder, the mean is simply the average of a random variable and is a measure of central tendency of the probability density of X. Its standard deviation is the square root of the variance, where the variance is the sum of the square deviations from the sample mean divided by the sample size n minus 1, as 1 degree of freedom is lost when the mean is calculated. The standard error of the mean, or simply standard error, indicates how different the population mean is likely to be from the sample mean. The standard error is the standard deviation divided by the square root of the sample size. When testing the null hypothesis that the two group means are equal, against the alternative hypothesis that the two group means are not equal, we can equivalently write the null and alternative hypotheses as the differences between the two group means are equal to or not equal to 0. The test statistic is then formed by taking the difference in the two group means, subtracting the hypothesized difference, which in this case is 0, and then dividing this quantity by the standard error of the mean difference, which is given by this expression. This test statistic will follow a t-distribution with n minus 2 degrees of freedom, where n is the sample size and 2 degrees of freedom are lost for estimating the two group means. Typically, the test statistic is translated into a p-value using the appropriate reference distribution, the t-distribution with n minus 2 degrees of freedom in this case. The p-value for a hypothesis test is the probability, computed under the condition that the null hypothesis is true, that the test statistic will be as or more extreme as what was observed. Large p-values correspond to a test statistic that lie close to the center of the t-distribution. A small p-value indicates the test statistic lies in one of the extreme tails of the t-distribution. A decision threshold, called the level of significance and denoted by the Greek letter alpha, is a pre-specified value on the 0-1 interval such that if the p-value is less than or equal to alpha, the null hypothesis is rejected and we conclude our data provide evidence in support of the alternative hypothesis. If the p-value is greater than alpha, we fail to reject the null hypothesis. Because the p-value is calculated assuming the null hypothesis is true, we cannot accept the null hypothesis. Suppose for this two-class comparison, we calculated the group sample sizes, the means, and their variances. Those quantities may then be plugged into the formula to yield the test statistic, which in this case is 2.31. Of course, using the t.test function in R will yield the same result, but additionally provides that there are 14 degrees of freedom because there are 16 observations and we lose 2 degrees of freedom by calculating the two group means, and it also provides the p-value, along with some additional information. This figure depicts a t-distribution with 14 degrees of freedom. Our test statistic of 2.31 would be approximately here. Again, the p-value is the probability, computed under the condition that the null hypothesis is true, that the test statistic will be as or more extreme as what was observed. We can see the probability associated with getting 2.31 or a more extreme value. However, recall that we are performing a two-sided test, which corresponds to the alternative hypothesis that the two group means are not equal. Thus, we multiply this tail probability by 2 to get the p-value. The R code that yields this p-value can be seen here. This, of course, agrees with the p-value from the t.test function, where we requested the test assume that the variances are equal as reported on the previous slide. Usually, the resulting p-value is compared to some threshold called the significance level, which is denoted by the Greek letter alpha. If the p-value is less than or equal to alpha, we reject the null hypothesis. If the p-value exceeds alpha, we fail to reject the null hypothesis. If we use the standard alpha equals 0.05 level for our test, we would reject the null hypothesis and conclude that the two group means are different. We have been discussing a two-sample t-test, so it is important to note that the data must be from independent random samples from their respective populations. The data cannot be paired measurements from the same individuals or related subjects, such as subjects from the same family or household. In such cases, alternative inferential procedures should be applied, such as paired t-tests or mixed effects models. The sample size should be large enough, or in the case of small sample sizes, the distributions must be approximately normally distributed. When assumptions are not met, alternative hypothesis testing procedures, such as the nonparametric Wilcoxon rank sum test, also known as the Mann-Whitney test, or permutation-based tests can be used. Now suppose that you are interested in comparing K groups where K is more than two groups. In this example, We are interested in comparing samples that were hybridized to one of 4 different modules, so k equals 4, where here 16 independent samples were hybridized, 4 to each module. The gene expression data are provided for a selected gene. Now the null hypothesis is that the 4 group means are equal, and the alternative hypothesis is that there is at least one inequality. In this case, we use analysis of variance, which yields an F-test. When calculating the F-test, we use the group sample means and the overall sample mean, as well as the group sample sizes. If you are interested in how the F-test is calculated, the total variability, or total sum of squares, is partitioned as arising from 2 sources: the deviation from the estimated group level mean about the overall mean, which is the sum of squares due to group, and the deviations of the individual observations about their estimated group means, or error sums of squares. Dividing each of these by their degrees of freedom yields mean squares due to group and error mean squares. Then forming their ratio yields our test statistic. Under the null hypothesis, this test statistic follows an F distribution with numerator and denominator degrees of freedom corresponding to this calculation. Of course, R will perform these calculations for you. The sum of squares due to group is 31,471, and dividing this by k minus 1, which equals 3 degrees of freedom, yields the mean squares due to group. The error sums of squares appears in the residuals row, which is 66,496, and dividing by 12 degrees of freedom yields the error mean squares. Forming this ratio yields our test statistic. If given an F-test and the numerator and denominator degrees of freedom, the p-value can be extracted using this expression.